Hello and welcome to Thursday's edition of Cracking the Cryptic on another absolutely dreadful day here in the UK. I couldn't possibly go outside today because the weather is torrential, but I'm going to distract myself, keep myself inside by having a look at a puzzle called Lockdown by Dorlir. Now, I'm not sure this is going to be an awful lot easier than yesterday's puzzle. Yesterday I did this bonkers puzzle by Marty Sears, which was a Sudoku. This is at least a Sudoku. It's definitely got normal Sudoku rules applying, but it has 5 stars out of 5 for difficulty and apparently is beautiful, but the logic is quite unusual. Now that really appeals to me, so I'm hoping I'll be able to grasp it. Dorlir is a ferociously clever individual, a maths professor no less. Anyway, the rules are really short for this one. I think we've got palindromes, German whispers, and region sum lines. So if you know what those are, you're already good to go. But I will go through them properly in a moment or two's time when we try the puzzle together. I don't know why it's called Lockdown either. It's very symmetrical. It's quite beautiful, but there was nothing beautiful about Lockdown. I can tell you that. Or that Lockdown was, of course, when Mark and I started to do 2 videos a day. I mean, it's a long time ago now. It's getting on for 5 years, isn't it? So there's been quite a lot of puzzles solved in the meantime. Yeah, well, thank you very much for being on this journey with us. Do subscribe, all the usual chit chat things. What else can I tell you about? We've got there was a bonus video on the channel this morning at 10 a.m. My continuation of Monday night's Blueprints stream. So if you have been following that series, I completed that day. So I won't tell you what you can see. You'll be able to see how long the video is, and I won't tell you what happened, but that video is live on the channel for you to have a look at if you're interested. And I'm pretty sure we're going to be streaming next Monday 10 p.m. UK time. I will confirm that as soon as I can. Other news, over on Patreon, our brand new competition is running, themed on the Wind in the Willows. This was the state of play yesterday, where I think we're going to go over 1,000 solves of the first puzzle now. Let's have a look. Yeah, way over 1,000. Absolutely phenomenal. 172 solves of all the puzzles. Incredible. The idea is to help Mole with his advent calendar. These are all the chapter headings in the book, of course. So very faithful to the book. Lots of puzzles to do. It's quite approachable this month, so do get involved and have a crack at it if you haven't had a crack yet. Still got plenty of time. Closing date's the 20th of the month. Chance to win. Well, I always feel a bit weird saying this because I'm not sure how much this is actually a desirable thing, but it's an opportunity to come on the channel with me and solve a puzzle. So if that might appeal, that's another reason to do the puzzles. I've got 2 birthdays to do today, so let me look at my list of birthdays. Anthony, not me, not my surname. You've turned 46, I think, and I know this because your bridge partner and best friend Damon wrote to me. I think I remember you from last year. You're seriously good at bridge, aren't you? Don't you compete in like the national championships and things like that? I think you've just got back to New York City from a bridge tournament in San Francisco, which probably was the national championships. So I don't know how you got on in that. Well, I hope. Apparently there was plenty of Sudoku solving in between matches. And on your special day, Anthony, you're going to be having sushi. Well, that's acceptable rather than chocolate cake. And yeah, I mean, if you really, really just can't abide sweet things, and you can only have savoury, then sushi is the best thing to have. So it's the second best thing, Anthony, and I hope you have a great birthday today. Many happy returns. And then we'll go slightly north to Montreal, where Lorne, you've turned 24 today, and I know this because your girlfriend Sierra wrote to me and told me you've been watching the channel for 4 years, so almost since the first lockdown. And you are wildly good at Sudoku, I'm told as well. A recent graduate in mechanical engineering, and Sierra is incredibly proud of you. So, Lorne, I hope that is a nice message to get today. Many happy returns. I hope you can find some exceptionally well-iced chocolate cake. And with that said and done, let's turn our attention to doing some solving. Let's have a look at Lockdown by Dorlir, and I will read you the rules, which won't take long. We've got normal Sudoku rules applying, so we've got to put the digits 1 to 9 once each in every row, every column, and every 3 by 3 box. Box borders divide the blue lines into segments, each of which has the same sum. So those two cells sum to the same as those two cells, sum to the same as that one cell, sum to the same as those two, sum to the same as those two. And each line will have its own sum. It doesn't actually say that in my rules, but box borders divide the blue line into segments with the same sum. I mean, I've never seen a puzzle that has region sum lines where these all have the same sum. So, you know, if those added up to 12, then these would add up to 12 every segment. Oh, that couldn't work there. I'm not going to assume that. I'm not going to assume it. It would be very unusual. And I will clarify the rules as necessary. Each grey line is a palindrome, i.e. it reads the same in both directions. So if this was 1, 2, 3, oh, I tried to do 1, 2, 3, 4 and failed. Oh, hang on, that's not going to work. That's a very short. I thought the palindrome was longer, but it's interrupted. Sorry, it's interrupted by a green line here, so that didn't work at all. 1, 2, it's only 4 cells long. So 1, 2, 2, 1. And you can see if we read it from this side 1, 2, 2, 1. If we read it from this side 1, 2, 2, 1. That's a complete shank by me. Apologies. Adjacent digits along the green line, or I think it should say a green line, because there are 2. That's definitely a green line. Must differ by at least 5. So if this is the digit 1, this has to be at least a 6. It could be 6, 7, 8, or 9 to be at least different by 5 from the 1 here. They are all the rules. Do have a go. The way to play is to click the link under the video as usual, but now I get to play. Let's get cracking. Now, what do we do to start this? I get 2 given digits. Sorry, I was about to say... No, I wasn't about to say it. I don't know what to do at all. Whoa, this is bad. Sorry, I'm so sorry. I haven't got anything to... I was about to say something totally fatuous, like... These 2 digits are obviously repeating because of the palindrome, so those are the same digit, which means that digit goes in one of those 3 cells. But I mean, that is completely and utterly inane. I mean, this digit, whatever that is, obviously these 2 sum to it, these 2 sum to it, these 2 sum to it, and these 2 sum to it. Okay, so I suppose these 4 digits all have to be different, don't they? Which means the minimum sum of those 4 digits would be 10. So if I fill those with the digits 10, effectively that represents 2x, i.e. let's call this x. That sums to x and that sums to x. So 2x equals 10 implies this digit is at least a 5. So that is a tiny deduction. And the grid is so symmetrical, I can just apply that logic down there as well. Let's get rid of the colour for this one. I'm about to get desperate here and resort to set, because I can't see anything. And normally if I can't see anything and it feels like all the lines are too short, there's normally a set trick to be found. But could we do... I'm not seeing anything else here. 2-cell region sum lines, you know, which are equating with each other, are just not interesting. The given 5 helps not one iota with a German whispers line. A German whispers line can't have 5 on it anyway, because if you put 5 on it, the next digit has to be 5 different from 5. If you go downwards, you get to 0 and negative numbers. If you go upwards, you get to 10 or higher, and they aren't Sudoku numbers either. So I don't have a Scooby-Doo. Right, okay, so I'm going to try set. Now set, if you're not familiar, set stands for set equivalence theory, and it's a geometrical idea, or technique, I suppose, that you can... Well, it's the origin of things like the Fistomerfell ring. If you've never seen that, that's a theory, or a theorem, that states that those digits in a Sudoku will always be the identical digits to those digits. And you can prove that using set. Now, that doesn't look useful here, does it? But yeah, I mean, the idea, I presume, is to try and put... Yeah, so if I put these 2 cells on a palindrome in a different set to those 2, I could yeah, I'm going to do that. Okay, so we'll do... Yeah, we'll do those cells against these cells. So let's just have a think about what that might be doing. So that's going to mean we could delete everything there, and I'm left with a whole load of nonsense. Oh, okay, so no, hang on, I should just do it down here as well. Yes, that's what I should do, because that's, okay, that's going to do something on the region sum lines. Right, I think it is set, it's just not what I've done there. So what my brain was trying to do there was to say, can I find some parts of the grid which I know contain the same digits, or the same sets of digits, and very obviously those 2 cells are the same as these 2 cells. So what I was looking at was this. But I'm actually going to extend it right across the grid. Let's highlight these cells in indigo, and the way to explain the logic is to say, what do we know about these indigo cells? Well, we know there are 36 of them, because that's 9 complete columns of the Sudoku. And actually we know exactly what the population of those 36 digits is, because it's 4 complete columns of the grid. So there's going to be 4-digit 1s, 4-digit 2s, 4-digit 3s, all the way through to 4-digit 9s in these indigo cells. Now, to try and offset this, what I'm going to also highlight, therefore, is these cells. I'll do those in a different colour. Now, can we describe exactly the contents of the orange cells? Well, there are 36 orange cells, and actually that's 4 complete rows of the grid. So the contents of orange and the contents of indigo overall are identical. We've got 4 sets of the digits 1 to 9 in each of the colours. But here's the kicker. What would happen if I removed this cell from both sets? Well, now I can't describe absolutely precisely what's left in orange and what's left in indigo, because I don't know what was in this cell or what will turn out to be in this cell in the correct solution. But I do know that orange and indigo are still the same set of digits overall, don't I? Because they were the same thing. They were 4 sets of the digits 1 to 9, and I just took exactly the same thing out of both. So what's left in both is the same. Now, look, so I can do that for all of the cells that have 2 colours in them. So let's start with that, but I think I can go much further. And basically everything's going to cancel here, because look at the palindrome here. Whatever these 2 digits are, they're the same, aren't they? So I can remove these 2 digits from orange and from indigo, and I know that what's left in orange and what's left in indigo must still be the same, because I've just removed exactly the same from both, and I can do that for all palindrome cells. So all of these palindromes, it's very pretty, isn't it? All of these palindrome things just disappear. Yeah, and now okay, so now what we're going to do is we're going to change tack slightly. And we're not, so at this point in the puzzle, it is legitimate and correct to say that what is in indigo, the exact digits that we have in indigo, are the same exact digits that we have in orange. Therefore, if I sum indigo's digits and I sum orange's digits, I'm going to get the same total. But that allows us to do more logic, because if I remove these 2 cells from orange, whatever they total, if I was to remove those 2 cells from indigo, I would be removing the same total digits from both. So I wouldn't be able to say, if I delete these from orange and delete these from indigo, I can no longer say that the exact composition of the digits in orange and indigo is the same, but I can still say that the sum of what remains in orange and the sum of what remains in indigo is the same. So I'm going to do that. I'm going to remove all of these pairs. All of those can go. Oh no. Have I just proved that 1 equals 1 here? So now I've just proved that... Oh dear. I'm sorry. I don't think that's worked, has it? I've got 4 oranges. So I know the sum of these 4 oranges is the same as the sum of those 4 indigos. And I know that they share a region sum line there, and they share a whisper here. Oh dear, I mean, I don't see what that's doing. Is that doing something? I'm just going to play with this slightly. Just to try and understand what this relationship means, because at the moment I don't understand it. So at the moment I've got 4 oranges equaling 4 indigos. I'm going to mismatch the sets now. So I'm going to highlight this row entirely in orange. Now the effect of that is now going to be that obviously what we've got in... Let me just double check. No, the middle wasn't. Okay, so the middle wasn't in. So now I've actually got 45's worth of digits more in orange than I've got in indigo. How do I know it's 45? Well, if you've been with the channel a while, you will know this. But there is a secret in Sudoku. It's something I share with only my very favourite people. But if you're watching this, you're definitely one of my favourite people. The secret of Sudoku is that a complete row of the Sudoku sums to 45. And I know that because it's going to have the digits 1 to 9 once each. And that's what you get if you sum the digits 1 to 9 once each. So we had exactly the same in orange and indigo. And I've just added another 45's worth of digits to orange by highlighting the whole of this row. But you can see I've got some duplicates here, so I can take these out. And now I've managed to eliminate all the indigos. And I've got the situation where what's left in the grid sums to 45. Because we knew that orange was beating indigo by 45. And the fact I've now got no indigo cells left, but I have got oranges left, means these sum to 45. Which I think is still... I can see I can put those up there. I'm sure I'm not doing this right, whatever I'm doing, because this is bonkers complicated. So what I'm thinking now is, I know these two oranges sum to the same as those two. So if I remove those from orange and add those in instead, I've still got 45's worth of orange. So now I know those two digits sum to those two digits, don't I? Because I know that orange overall sums to 45, and I know column 5 sums to 45. So those add to the same as those. Oh, no, yeah, that's it. That is it. That is it. I've done this wrong. I've done this wrong because that was so complicated to arrive at that result, but it's very pretty now. I've got it. Okay, can you see why this matters? So what we've deduced from all of these mad sets I've been drawing is that this domino sums to the same as this domino, and yet look at the green line here. Now, I alluded to a secret about green lines earlier, that they didn't have 5 on them, but there's another secret that's very important about green lines. And that secret is this sort of what we call this oscillation of polarity. Because you can't put 5 on a green line, the digits along a green line will oscillate. They'll either have the quality of being below 5 or above 5. So let's imagine this one is below 5. What's this one? And the answer is, we don't know exactly, but we know for sure it's not a 1, 2, 3, 4 digit. Because if it was, these two digits cannot be 5 apart. So this would have to be from the 6, 7, 8, 9 portion of digits. And then this one couldn't be from the 6, 7, 8, 9 portion of digits, because these can't be 5 apart. So this, again, would go back down again. But that matters here. It matters. Because we've got the situation where these two digits, the sum of these two is the same as the sum of these two. And yet, these two are different from a polarity perspective. Why is my watch posting? That's fine, it doesn't matter. In other words, I mean, imagine this was a ridiculous digit. Imagine that was 9. Then you've got 5 plus 9 is going to equal this digit, which we know is low polarity if we've made this high polarity. The maximum that could be is 4. So we're saying that 5 plus 9 is equal to 4, or could somehow be equal to 4 plus 3. It's just not going to work. The only way I can see this working is by squeezing these digits as close together as we can from the two sets. So we could make this the biggest low digit we could have, which would be a 4. And we could make this the smallest high digit we could have, which would be a 6. These are now of the correct polarity. And we would have a situation where 9 equals 9. There's no other way to do it, is there? The moment we lower this will always beat it. Yeah, and it's simply the only way to find equilibrium is to squeeze these digits close together. I mean, it's a breathtaking, actually. That is a really weird. It's really strange, but anyway, we've got it. So that's got to be 4. That's got to be 6. 6 can only go next to 1 on a whisper. It's the only digit that's sufficiently different. 9 can only go next to 4 on a whisper because it's the only digit that's sufficiently different. And we've actually, this can't be a 6 now by Sudoku. No, that doesn't work there. And we've actually got ourselves off to the races. Now, is there any value to this orange now? I doubt it. No, I was simply proving those were equal to those. Okay, so I'm going to get rid of orange. I think that is the break-in that we were trying to establish. And I mean, it's a good trick, to be honest. If you can't see anything and it looks impossible, think about set. And I'm sure I got the wrong set there. It's not that there's necessarily that there will be a way that I could have distilled that relationship down by picking a better way to think about it. But we built it up gradually. we could see that there was something going on between the palindromes, and then eventually I realised that I had to build up bigger, more of the grid in sets, and then you could offset the region sums as well. That bit in the middle was weird. That was weird because I couldn't see it. Which digits was it? Was it those against these? It might not have been exactly that, but should I have been able to see from that there was that equivalence, that these digits had to be 4 and 6? I don't know. I still don't know now, looking at that, why I should have known that. That's weird, isn't it? Anyway, we got ourselves off to the races. So let's see, how do we do this? This middle digit now sees 6 different digits, so that's got to be 2, 7, or 8. And okay, I presume it's this one, is it? Is that what we have to look at now? The thing is, there's absolutely nothing in common between these 3 and these 3. So it's not like I can even identify one single digit that can't go on there. Now, I'm not sure. Maybe this isn't where we look. Maybe we've got to look at... Oh, Maverick's flying over. Hello, Maverick. What else could we do here then? Good grief, I don't know. Oh. No, okay, well, I can't put 9 on this line, because this total can't be bigger than 9 as a single digit total to this region sum. So if I was to put 9 here, even if I accompanied it with 1, the region or the segment total would be 10, wouldn't it, or higher, and that couldn't go in this cell. So 9 is in a domino in box 8. It can't go on the region sum in box 7 at all, unless it's there. It could go there. So it's in one of those 4 cells. Yeah, it's not. Yeah, that's interesting, actually. That is interesting. So where is it in box 4? And the answer is it's in lots of places. It's in those places. But actually that means in column 1 it's a bit restricted. Because if it's there or there, it's on the palindrome and it's going in one of those 2 cells. So 9 in column 1 is in one of those 4 cells. But let me just colour that for a moment. So the 9 in column 1 is in one of those. Does that work here as well? So the 9 in this box can't go on the region sum, can't be in its own row. So the 9 is in one of those cells. And if it's on the palindrome, it gets transported down here. So the 9 in column 9 is in one of these cells. So the 9 in box 9 and the 9 in box 7 are in a 2 by 2. And the 9 in box 2 is in one of those cells. No, that's not true, because this is different. This one could have a 9 on it, couldn't it? And the reason for that is that this line we're not adding to a single digit total. So we can't use the same logic I've been using to keep 9 off the region sums in these 2 boxes. bobbins. Okay, so no. Oh, okay. So 9 in box 3 then. Because yellow contains a 9, 9 in box 3 is also in a 2x2, so it's always in 2x2s. But does that matter? I don't know now. This is I don't again. I think I don't think I've grasped this puzzle at all. If I don't know. How am I meant to do this? I could certainly... Okay. Okay, rather than thinking about this box, where's 9 in row 1? I will think about that. Yeah, I'll think about that. Where's 9 in row 1? It's not there because of my yellow marking, so it's not here. It could be there, I think. It could be there, it could be there. It can't be here. It can't be here, and because of my yellow marking in this column, it can't be there. So it's in one of those 4 cells. Let's just use a slightly different colour to say that. That's a horizontal 9. And that's quite... So I now can say 9 is not on that little strand here. Because... yeah, if 9 was here... you could... yeah, it's very odd, this. If 9 is on this... maybe this is the way to see it, in fact, more quickly. But if 9 is on this strand... you actually now can't put 9 in row 1. Because you've ruled it out of here, those 3. You've ruled it out of those 2 because of this region sum single total. You've ruled it out of there from yellow. You've ruled it out from there from yellow. And if you were to put it here, it would get transplanted by the palindrome here, and I get 2 9s in box 2 again. So 9 in box... 9 in box 2 is in one of those cells. And in box 8 it's in one of those 2. And that's going to be very important. I don't know. I'm going to make those 2 orange to be consistent with my orange highlighting. It's weird. Oh, I see. It's because I get a 9 that the 9 is a lot more restricted in row 9 compared to row 1. The symmetry does break a bit because of this 9 that I've got in the grid. Has this helped me though? It was weird, that's for sure, but it hasn't got me any 9s. It's kept 9 off there. Yes, okay, so this line doesn't have 9 on it at all. Which I don't think is going to be very important, is it? Is that going to help me? I mean, it means that this total is not... well, it could never have been. It could never have been a total that required a 9, because I could never have made that domino add up to anything useful. Yeah, the problem with this line is that it's essentially got an absolute plethora of possibilities for its 2 cell segments. You couldn't have anything that required a 1 here. So the minimum these 2 digits would be 2 plus 3 is 5. 5 I think is possible. No, actually 5 isn't possible. 5 isn't possible, but only because of this domino. If you did try and make this segment add up to 5, this segment couldn't work, because it couldn't be 1 4 or 2 3. Actually 6 doesn't work either. 6 doesn't work because of the 4 5 here. This couldn't be 4 1 or 4-2 or 5-1. And if it was 7, could that would have to be 2-5, and that would have to be 1-6. And so this would have to be 3-4, because it couldn't be 2-5, and it couldn't be 1-6, because obviously this cell couldn't be 1-6 and that cell couldn't be 2-5. So if it was 7, it would be very specifically 1-6, 2-5, 3-4. I don't see what's the problem with that. Yeah, I'm not sure. This would add up to 21 if it was 7. Eight doesn't work, actually. 8 doesn't work. Maybe it's 7. Maybe it's 7. 8 doesn't work because this domino can't add up to 8. It can't be 1, 7, 2, 6 or 3, 5. Right, I'm going to make a... Where shall I put it? I'll make an aid memoir. 7 works as a total for this line. 8 doesn't work. What about 9? 9, this domino would have to be 2... no, that could be 2, 7 or 4, 5. And that one could be a lot... Oh, 9. Okay, sorry, this doesn't look very good immediately. 1, 8 and 3, 6 would be ruled out. Right, so I think 9 is possible. 10. 10 would be very difficult here, because this would have to be 2, 8, I think. It couldn't be 1, 9, 3, 7 or 4, 6. That would make the middle digit a 7. That would make, if that was 7, this would have to be 2, 8 as well. So if it was 10, that would be 2, 8, and that would be 2, 8. And that might not work for some Sudoku reason. That would be 7 in the middle of the grid. What would those two add up to? Well, they would add up to 10, but they couldn't be 2, 8. They'd have to be 4, 6. Ah! That would have to be 6 here, 4 here. This is getting out of hand, isn't it, I think? So 10 works as well. I can't even write 10 into the grid. I have to use my hybrid way of writing 10. Okay, so 7, 9, 10 work. 11. 11 would have to be there. It would be restricted. It couldn't be 5, 6, 4, 7 or 2, 9. It would have to be 3, 8. So if this was 3, 8, this one though, that could probably be 2, 9 or 4, 7. Oh, no. No, actually, that's wrong. If this was 3, 8, this cell... Oh no, it's still fine. Sorry, I was thinking I could get rid of an option because of the middle, but I can't. Oh, okay, I can't see how to do that. So I think 11 is also possible. I'll write it there so it doesn't pollute my 9 pencil mark. 12 is not possible, actually. And that's because this domino couldn't add up to 12. 3, 9, 4, 8, 5, 7 doesn't work. So 13, is that impossible? 13, that would have to be 6, 7. No, I'm not doing it. I'm not even referring to it. That would be 6, 7. Oh, that one can't have... that doesn't work. 13 is impossible, but that's very hard to see. The reason 13 is impossible is this becomes impossible, these two here. Because if this is 6, 7, what's this? So let's just pencil this in. This one hasn't got 9 on its domino stub, and it hasn't got 6, so it's not 6, 7. So that has to be 5, 8, and now there's nowhere to fit. There's no fourth way of making 13. We couldn't, these can't be a 6, 7 pair because this cell couldn't exist. These can't be a 5, 8 pair because this cell couldn't exist. And they can't be 4, 9 because there's already a 9 in the box. And we've run out of ways to get to 13. So 13 doesn't join our list of possibilities here. Now 14 is going to be tricky, isn't it? No, I just don't think it's possible, because don't there axiomatically need to be 3 ways to make the totals? Ah, no, that's wrong. They don't. But they do in 14's case, because these will be different. But you could have the same stubs there. But you can't actually do that here. So 14, this would be 6, 8, wouldn't it? Because it can't be 5, 9. And this would have to be 5, 9, because it can't be 6, 8. And they are the 2 ways of making 14 in a domino. And now you've got no way to fill that domino. That's lovely, actually. So 14 isn't joining our coterie of digits. 15 would have to be a 7, 8 pair here. Yeah, and then that's got no way of being filled. Because these two would have to add to 15 without using 9. They have to be 7, 8. And now, what domino are we making this to add up to 15? It can't be 9, 6, and it can't be 7, 8. That would kill this square. So 15 doesn't work, and I know 16 and 17 don't work, because they would require a 9. So actually, you're only looking at 4 options here for this domino, or for the total for this line. 7, 9, 10, 11. I'm just going to go back and look at 7 again, because that was, I remember when we looked at it, that was restricted. So if we look at 7, this has to be 1, 6, because it can't be 3, 4 or 2, 5. This has to be 2, 5, because it can't be 1, 6 or 3, 4. And this, yeah, this is the one where this had to be 3, 4 in the middle, because it can't be 1, 6 or 2, 5. So it has to be the third way, and that would have to be the way that this would look. Now, does that fail or not is the question. And the answer is, sorry, I just stopped talking. I don't know, actually. That could work. Is that doing anything interesting at all? The thing is, it's weird, actually. I have a horrible feeling that even if you knew, even if somebody was from the future, Simon from the future, hopefully, who could solve the puzzle, came back and said, Simon, these are all correct, well done. I mean, how does it help me? I mean, it fills some digits in, but it doesn't, I can't see what you then do. I've got a horrible feeling I'm still doing this puzzle wrong. It can't be what we were looking at before, can it? What was it? Those cells. Those cells were the same as these cells. I don't think that's it. I think even though these are 1 and 9, there's still so much flexibility in the other values. What on earth have I got to do here? It's not that green line. It can't. That green line, I think, the puzzle is very, very symmetrical, isn't it, around the negative diagonal. If I was to draw a line down the negative diagonal, apart from the 3 and the 5 being different, obviously, that green line is going to cause an imbalance But everything else is the same. I mean, oh, I don't know. I feel like that's a disambiguating green line. Right, here is a different question then. This is probably not how to do it either, but so far I've been very, very good at coming up with these things. I can't even see what this does. What I've noticed is in this column, those digits, you can sort of, you know where they go, I think. Because this little coterie of digits, obviously they can't go in their own box, and they can't go on the palindrome here. Because if a purple digit is on this palindrome, it gets transplanted back into box 4 again. There would be 2 instances of it in box 4. So those digits are exactly the same as those digits. Now what that means... Yeah, see, that is interesting. That's interesting in the context of our ideas over here. Because actually... We know those digits add up to the same as those, don't we? So actually we know that the region sum total for this thing, whatever those two add up to, these two add up to in column 1. I'm not actually saying they're the same digits either, because imagine that was 1, 6, which is what it was when we were thinking about this total being 7. If that's 1, 6, is it necessarily the case that that is a 1, 6 pair? Given that these... It's not the same. No, it's not. Because if this region sum added up to 7... Yeah, if that was 1, 6... that could be 2, 5. And now these could be 2, 5. So we... So we don't necessarily know. I don't know that those 2 digits are in those 2 cells, but I do know that those 2 digits sum to those 2 cells. That I am prepared to commit to. And presumably that is symmetrical, in the sense that that must apply here as well. So those digits, where do they go in row 1? Yeah, they share that digit. Yeah, okay, so that's very interesting. Yeah, this is a weird point I'm about to make now. So now I'm going to allege that this digit is the same digit as that digit in this puzzle. I think that's true. Because, how can I show that? Imagine these 2 sum to x. Then these 2 also sum to x, don't they? But we know from our logic, we worked out that the sum of these 2 is the same as the sum of those 2. And therefore, the sum of these 2, because this total is the same as that total. So the sum of those 2 is the same as the sum of these 2, and that's common to both sums. So imagine this was 7, and imagine that's a 2. Well, both of those are going to be 5. To make them both add up to 7. That's just how maths works. So these... Oh, I don't know how to do this, because now my 7 is going to get overridden. I'll move my 7. I'll move my 7 here. And I'm going to say those 2 digits, I'm going to call them x. There we go. So I've got X in the corners. Now, and what does that mean? Maybe not very much, actually. Wait a second. Hang on. Hang on. Yeah, I think I'm getting closer to the idea of this puzzle actually now, with what we're doing now, rather than everything that I've done in the first 50 minutes. Goodness, that's just flown past. Because I think these 2x2s, I've just noticed this 2x2 and this 2x2, I think I can play the same trick. Because although this isn't it's sort of, I could almost view it as a region sumline, because I know that's, I mean, I could sort of draw that through there and that through there, and it's the same logic that we've just been doing, isn't it? Except it's better, because I know those add up to 9. Yeah, I think this is right. So what I'm thinking now is, I'm running out of colours here, I'll make these red. But where are these digits in row 9? Now, we know they can't be here, because they get transplanted onto the palindrome, and they're not in those cells. So these cells are in these positions. But, again, I know those two have the same total as these two. So I know these two must have, I'm not saying they're the same digit, but I'm saying that the total of 6 plus 3 is the total of X plus that digit. So these two digits add up to 9. Now, I can play exactly the same game here. Those digits are the same as these digits, and because these are the same as those two add up to 9. I don't know what this does, but this... I feel like it must... I feel like this feels like it's the thing. How do we use that then? So I know those two add up to these two. These two add up to those two. And these two add up to 9. And those two add up to 9. Wow, I don't know. If I don't know. I'm so sorry. If you can all see this, I've a feeling you probably can. What? Maybe I've got to combine this with the options I've got left up here, and that will help me to realise whether or not things are possible. If that was 7, i.e. if these were a 1-6 pair, what does that... We know they would be a 2-5 pair, don't we? Because they couldn't be. Now what does that do? That... I don't know, actually. I'm not actually sure. That's... I think it depends. It depends what it does. If... I know these add up to 9, don't I? Yeah, the reason this is very complicated is that... Yeah, this is going to be very complicated. If this turns out to be 7 or 9, it might be easier to disprove the higher numbers first, actually. Let me explain why I think that's the case. I think this might end up being 7. Or maybe it's 9 because these add up to 9. But I just want to have a think quickly, if it's all right with you, about 11 and then 10. And the reason I think they might be easier is... I'm not sure this is right. But if this adds up to more than that, then I think these two digits end up there. That must be logical, mustn't it? I mean, so imagine these add up to 11. Do we actually know what they are? Yeah, we know they were 3, 8. If these add up to 11, we've got to think about where these two digits and where they go in this coterie of digits. Now we know these cannot possibly add up to 11. So we know that one of these digits, at least, well, so is it possible these two digits are those two digits? No, because I can't write 11 in there. Therefore, at least one of these digits is on this string, and therefore both of them are. Because imagine this is a 7, and let's imagine that's 1, 6. Let's do something that has an overlap. Imagine this is 7 and this is 3, 4. The 4 would have to go here, so would the 3, and obviously that would then break. But the point is that if this adds up to more than this is capable of adding up to, then those two digits are those two digits. So in this situation, where this is 3, 8, the 3 and the 8 would go right into the corners, and we would get a 3 in the corner. Okay, and hang on, the 2, 5 is not relevant to this, is it? Because we're saying now these add up to 11. So the same logic applies in row 1. If this is 11, this is 11, and those 11s have to go here and here, because this can't equal 11. So if this is 3, 8, these digits are all from 3 and 8. I think. Now, is that... Oh. Well, hang on, and this would be 11 as well, wouldn't it? So 3, 8 here. No, hang on, this is broken. Oh, see, I'm so stupid. I am such a thick person sometimes. Yeah. So what I've just said, it's quite plainly wrong, this. It's not 11. And the reason is that if this is 3, 8, I've just literally said those digits are 3, 8. Because I know these two are the same by my X logic, and I know that must add up to 11 because that's what we've started this presumption from, this adding up to 11. So this is a region sum line, so this adds up to 11. Now if these are 3, 8, I know they're on this domino, because these two must be the same total, because I can't write 11 in here. And that means this is a 3-8 pair, but I've got a 3 in the column already, and that cannot be true. So this is not 3-8. That's impossible. And 11 is not the total. 11 is not the total we're looking for. Now, let's disprove 10, because I think we'll be able to do the same. If this is 10, well, where's going to be the easier place to look? Maybe this one, because if it's 10, that has to be 2-8. Because it can't be 1, 9, 4, 6 or 3, 7. So if it's 10, this is 2, 8. Which means, because this can't be 10, these are exactly the same digits. Which means this is a 2, 8 pair. Which means this is a 2, 8 pair. Which means this is a 2, 8 pair. We're going to have a 7 in the middle of the grid. This... Oh, we looked at this. That's going to be 4, 6. Hang on, though. And if this is 2, 8, we know those two add up to 9, so this is 1 or 7 in the corner. Oh. Okay, I'm so sorry. I don't know if I can get rid of that then. I thought I was going to be able to get rid of that. So I've only got rid of 11. I haven't checked 7 and 9, but I think 7 and 9 are going to be more difficult to disprove. Let's go back. Okay, let's go back to 7 again. So if this is 1, 6, we know that's 2, 5. Maybe there's something that says these have to be the same. But the reason I think this is more complicated is that we then have a decision to make about this region sum line. Because yeah, I mean either these two digits here are a 1, 6 pair, or whatever they add up to goes there. Because I can't only put one of these digits on here, because these have the same sum. So if I put one of them on here, they both go on there. And if I put one of them on here, they both go on there. That must be true. If I put one of them on there, yeah, I can't put one of them. I can't put one of them on there. It doesn't make sense to do that. If I put one of them on there, I put both of them on there. So if I put any one of them on there, I have to put both of them on there. That's totally and utterly logical. I'm completely happy with that now. Right, but I don't know because this could be a 7. I think it's more difficult to disprove this. Alright, let's assume that these are the same. Then the 1, 6 would go here. This would be a 1 or a 6. What's that doing? I don't like that. That feels wrong. I can't even articulate why it feels wrong, but everything in me is saying, no, you've broken the puzzle. Have I? I don't know. I might have done. Let me just think this through. So if this is 1, 6, this is 1, 6, this is 1, 6. You can see there's no coincidence between 2, 5 and 1, 6. So this 1, 6 pair here would end up in that domino. And okay. And what would that corner digit be then? That would be the complement of 1 or 6 that sums with it to add up to 9. So it would be 8 or 3. I mean, that doesn't work, but for the most peculiar reason. yeah, it's very hard to to explain this, but it doesn't work, and it's to do with. There's a better way of explaining this. I can see a way of explaining it. I can see a way, and I will share that with you. I'm just trying to think about whether or not there is a general point here that it is just eluding me. If this is 1/6, this is 1/6. This is 8/3. 8 or 3. I wouldn't know which. Okay, I mean, I'll explain how I've seen it breaks. So, if this is a 1/6 pair, where am I putting 2 and 5 in the top row of the grid? They've got to go in there somewhere. And that means I think they have to go here. But now, by Sudoku, where am I putting 5 in column 9? If there's a 5 in that domino, it can't go on the palindrome because it would get transplanted back into this box, so it has to go in the corner. And 5 can't go in the corner because the corner in this world, this digit is a 3 or an 8. It's definitely not a 5. So it doesn't work. But I mean, I appreciate that's complicated, and it hasn't got to the end of this. Because we still could have 7 working, because what we did there was we said, okay, I'm going to imagine that the 1 and the 6 go into those 2 cells. But it's possible, isn't it, that the 1 and the 6 go here. Although that's going to give me that's going to give me the same problem, but the geometry is going to swing the other way then. This is incredible, actually. Because if I make this a 1/6 pair, now this 6 is forcing this to be a 6 in the corner. Oh, in fact, that might do it straight away. Because if I put 6 in the corner, I know that X is now 3. I get 2 3s in the corner. I'd be singing a lot. But the problem with that is it doesn't work. And you might say, why doesn't it work? Well, the reason is complicated again. But if these are 3s in the corner, I've got to put 3 on here because this is definitely a purple digit. I know from the region sum this is 7, so this is a 3-4 pair adding up to 7, which means this 3 is complemented by a 4 here. So I've now got 3 and 4 in these cells, which have to find a home in green. So this is a 3-4 pair. This is a 2-5 pair because green has to have 2-5 in the top row. And that 5 is again putting a 5 in the corner, which we started by noting would have to be a 6. And that doesn't work. So it's wrong. So 7 is now off the agenda. I mean, this is absolutely brilliant as a puzzle. It's just very hard because the way, I think it's the way I'm approaching it. Here's what I think. I think I've uncovered an interpretation of the geometry that lives in the puzzle, that Dorlir has baked into it. I've uncovered a way of thinking about it which allows me to see how the logic can be found, that can solve, or at least get a bit further in it. But I'm not sure I'm able to articulate it as beautifully as it might be possible to articulate it. And that makes me a bit anxious, because I always love to show these puzzles in the best possible light if I possibly can. But anyway, I'm now going to think about 9, because if I can rule 9 out, which is going to be difficult, I think, because I think 9 is probably the most complicated case, because I don't think we know what these dominoes are going to be in the case of 9, and 9 could be there. So it's going to be difficult, but let's have a think about, if I can rule 9 out, we know the number's 10. So if it's 9, where do I start the thinking from? If it's 9, I know these add up to 9. And I know those add up to 9. So now I know these two digits are the same. So if these add up to 9, those two digits are the same. And I don't know. I don't really know how to start to think about this. Maybe it's here. If that's 2, 7, or no, 3, 6 won't work. 4, 5. So this would be 2, 7 or 4, 5. And these, if this is adding up to 9, I know these add up to 9. I know these add up to 9. But I don't know about this thing here. I would love to be able to just cut through this and come up with some sort of explanation. I think there is a way of doing this. I'm just brain is not capable of doing it on the fly. Come on, Simon. How do I do this? The middle of the grid, if it is 9 on this segment here, neither of these can be 4, 5, neither of these, that's going to help me. Right, if it's 9, actually this might be correct. Because neither of these can be 4, 5, and neither of these can be 3, 6, neither of them actually can be 1, 8 either. So in the situation where this is 9, this domino here has to be 2, 7. It has to be. That's all it can be. And the middle digit would be 8. So it would be in this world. And that feels much more manageable. Yeah, this is much more manageable. Because now, if this is a 9 total, I know what this is. It's not 2, 7, 1, 8 or 4, 5. So that is 3, 6. And I must know what that is. That's 4, 5. That's the only way of contributing these. These are now different, which is not the situation we ended up with if this was 10. Well, okay. And here, if this was 3, 6, I know that's not going on that domino. Because if it goes on this domino, where are we putting 3 and 6 in row 9? They both have to go in that cell. And this is not a Schrödinger cell. It cannot simultaneously be 6 and 3. A concept so ridiculous I cannot tell you. So the only way that this works is if this is adding up to 9, the 3 and the 6 go into the corners, which means these are all 3s and 6s, which means this is a 3, 6 pair. So this would add up to 9. So this would be 3, 6, this would be 4, 5, and that doesn't work. For the same reason. This is beautiful, because if you do have to put 3, 6 there to make this one work, that one becomes 4, 5, and that matches off here with this 4-5 and puts a 4-5 Schrodinger in the corner. So you either end up with a 3-6 Schrodinger or a 4-5 Schrodinger. And he can't make it work. So it's 10. There we go. Simple. Not. That was not simple. That was very hard. But very, very... Oh, I'm so chuffed with that. So this is 10. It's the only thing that works. And... Right, and that has to be 2-8. It has to be. Which makes the middle digit a 7. And that's because 1, 9, 4, 6 and 3, 7 don't work. Which makes the middle digit a 7. Which makes this not 1, 9, 3, 7 or 4, 6. So this is also 2-8. And now somehow or other, we've got to crack the puzzle from here. So now these two digits are 4, 6. Because they can't be 2-8, they can't be 3-7, they can't be 1-9, and I know the order, so I get more digits. 4 there, 6 there. This row needs a 1-3 pair. This column needs a 5-9 pair. Okay, and this is great news. Is it? Maybe. Yeah, well, this is going to do something. Because now I know that this domino here has no interest in being overlapping with this. Because I can't write 10 into this. So this domino has to go into both of those cells. So which means this 2-8 pair goes in these two cells exactly. And therefore, and that logic must also exist in the top row. Those two have to go in there. So this is 2 or 8. And now this is the complement of 2 or 8 that sums to 9 with it. So that is 1 or 7. Okay, we can get rid of our... Oh, no, we've got to be careful. Get rid of those pencil marks, because we now know we're definitely looking at 10 on this one. Now. Yeah, this is lovely now. This is lovely, because now I simply ask the question, where does red go in row 9? 3 and 6 are not allowed to go in these corner cells, so they've got to go there, and therefore that region sum is a 9. Bingo, that's not a 9 anymore. And that logic works exactly the same in column 9. Where do 4 and 5 live? And the answer is there. So this is now a 9, which means that is not a 9. That is not a 9. 9 is in one of those 3 cells of box. Let's just double check that, yeah. Now, can you put it on the palindrome? No, because it would get transplanted here into its own column, so it's not there. That logic is symmetrical, so it can't go there because it will get transplanted here. So that is 9. This is not 9. 9 is in one of 2 places in box 6. It would be absolutely beautiful if this now actually yields its secrets. Oh, it's going to. Yeah, where's 9 in box 1? Again, it's the same sort of logic. It can't go on the ends of these palindromes because it would get transplanted into a naughty position. So this has got to be 9. That's not 9. That's not 9. So 9 is now... okay, maybe 9s are going to run out of momentum. But that was still great. That was still great. We're still very happy with that. This domino is made up of whatever, it's these two adding up to 9. So this is either a 1-8 pair or a 2-7 pair. Okay, I don't think I know how that works. This domino adds up to 9. It's not 1-8, it's not 2-7. So that is 3-6 or 4-5. And that domino is a purple. So that's got to find a home in this column, which means it's there. 3, 6 or 4, 5. That one is not 6, so this one is not 3. Oh, in fact, look, there's a 3, 6 here. So we actually know these are 4, 5, which means these are 4, 5. Which means 5 is in one of these. Yeah, I think I've just got to be a bit diligent here. This one is also either 1-8 or 2-7 from these 2 cells. But can I, how did I just do that lovely logic that we found over there? I used this 1 and this 2, 8. Does that, so there's a 2, 8 there. Yeah, that does the same thing here, doesn't it? This domino can't be 1, 8 or 2, 7. So it is 3, 6 or 4, 5. Oh, hang on, did I? I didn't treat this as a palindrome, did I? I'm worried I did. Oh, I've got to go back. I'm not sure. I've got a horrible feeling. No, I didn't treat it as a palindrome. I just used the fact that it was the pink digits in this column. That wasn't. I didn't say it was a palindrome. So I am happy. I'm happy, and I can do the same here. The green digits have to find a home in row 1. So they are there. They're not 4, 5. So they are 3, 6. This is 3, 6. Oh dear. Okay. Now, I don't know what to do now. It's going to be something like, where do... Can I use any more of my trickeries to help me here? I think I'm tempted to remove some of my trickeries. Tempted to remove the... Oh, no. I was going to remove the colours, actually. These two are definitely those two. Those two, they can be... that's not helping me. These two are those two. These two are those two. Those two aren't... That's not helping me either. Oh dear. It's not this whisper thing, is it? That one can't be... Oh, it can never be 5. So it is slightly... Oh, it can't be 4, actually, because that will put 9 on it. What's this cell? That cell could be 1, I think. Can't be 2, because there's a 2, 8 pair in the row. Can't be 3. Can't be 4, because that would put 9 on the other side of it. Can't be 5 by whisper logic. Can't be 6. Might be able to be 7. Can't be 8, because 8's in the 2, 8 pair. And it can't be 9. That is 1 or 7. So, if this was 7, this would have to be 1 or 2. Actually, these have complements as well on their palindromes. Let's make sure we don't neglect that. Oh, wait a second. Right, there's a 1, 7 here. There must be a 1 or a 7 in this red domino, because it's either a 1, 8 pair or a 2, 7 pair. So whatever this 1 or 7 is that lives in that domino, that's got to go there in box 2. Now I've got a 1, 7 pair in row 1, and these digits are from 4, 5, 9. And I know that that's not a 9, so this is palindromed. Oh. Nah. Okay, maybe that isn't. Well, that was very... I've got 4, 5 pair now in column, in row 2. And I know this digit is either... If this is 7, this is 1 or 2. It's not 2, is it? Because I've got this 2, 8 pair. So if this is 7, this is 1. But if this is 1, this could be a high digit. So it could be 6, 6 or 7. It can't be 8 because of the 2, 8 pair, and it can't be 9. So it's really restricted. It's really restricted. And it goes there on the palindrome. Now what does it see in that domino, I wonder? Don't know. I'm not sure. What's the colour of that? What's the colour of parsley? I don't know. Is it something to do with 1s and 7s? That's what I feel like it might be to do with. I know there's something there is transplanted there. That's different to that one. And I know that one is the same as that one. And so that one... I can't quite see this. I feel like I might be able to get both versions of 1/7, either looking at that or looking at that somehow, which would make that a 6, which would be terrific. Just don't quite see how to do it. Maybe, okay, let's get rid of my original orange, because this was all predicated on positions of 9s, which I think they've all become a bit obsolete, haven't they? And let's just try and colour. I'm going to try and colour 1s and 7s against each other, so I'll make that yellow. So that's definitely orange. There's definitely a yellow in there. And the 1 or the 7 that lives in this domino, I know is that digit, don't I? Because it has to appear in row 9. So this one, yes, and now I'm going to use that again. And now I've done it. That's so brilliant, Dorlir. You are a total genius. It's a total genius, because now, yeah, by the logic of this domino having to be in there, I now know yellow lives in here. Now, if yellow lives in here, I want to consider this digit, and I want to consider it in both positions, because this one, this 1/7 is yellow is looking at that cell, and orange is looking at that cell. So this cannot be either version of 1 or 7, and has to be 6, which makes this 1, this 7. This now is 2/7. Not 2/8, it's 2/7, which puts 7 in the corner, no song, 2 in that corner, 8 in that corner, 2 in that corner. It probably does other things too, but let's at least bask in a small amount of a win for the goodies there. Oh dear. Oh, I was really hopeful. Oh, 6 here. Okay, so that's 6, that's 3. That's not a palindrome, so we can't do anything terribly clever with that. 3 lives in one of those. Okay. So does this 2/7 do something? Or do I know what that one is? I know that one's 2/7 as well, actually now. So 2 has to go there in the middle box. For what that's worth, which might not be everything, but it's something. So what are these digits then? They are 3, 5 and 8. Can we do... How can that... Oh, there's a 3 looking at that one. There's a 5 looking at that one. Let me guess, there's nothing looking at this one. Yeah. Okay. Oh dear. Alright, so we can't do that. 1 is in that domino. What are these digits? 1, 7, 8. Okay, so that's not 1. Wow. I'm definitely still not finished, am I? Oh, here's 7. 7 has to go there, apparently. I don't trust this 9. Oh, no, the 9s. I did resolve a bit, didn't I? I think that's a legit... No, that is a legitimate 9. That is completely legitimate. So that means I get the 9 over there as well, which is great. Now in this column, where's 1? In column 1, oh, it's lovely. It's got to go there, which makes that 3 and that 3 by palindrome logic. That 3 puts a 3. Oh, it is working. Now I've got a 5-8 pair in this row. I haven't put 1 into it, so I shall do that. That's now a 3. Now in this column, what do we need? 6 and 8. And they're on palindrome, so that's really exciting. 6 is there, in fact. 6, 8, 8, 6. 8 goes there, so that's 7, that's 1. 8, 2. I've got a 4, 5 pair in this row. I've not put 7 into the row, so I should do that. 6 here goes 6 and 3. 2, 4, 5. How do we do it? 6, 6 and 3 are resolved. 7 and 2 are resolved. Okay, this is really getting exciting now. We need 3 and 4. Do not joke. It is exciting. That's a 4 by palindrome. These digits are 1, 2, 5. The Sudoku is still working, which is something, isn't it? So that digit goes there, and it's not now 2. Unfortunately, okay, we don't know. So it's 1, 5, or 8 to complete this column. And what do we think? I'm not sure. I'm not sure where to look, but oh dear. 4 here is good. 4, 5. So this row needs. This is good. This row needs 1, 2, and 7, and this digit sees 2, 1, so it's got to be a 7. Which means that's 7, that's 2, that's 1, that's 5, that's 2. Palindrome tells us this is 5, so that's 9, that's 5. 4, 9, 4 by palindrome, 4, 5. These two digits are 2 and 5, but the 4 here is going to be our friend. 5, 2, 2, 8, 8, 1. And that's 5, that's 8, that's 1, that should be 8. That is a spectacular puzzle, isn't it? If that's right. Yes. Yes, it is right. My goodness, it's another long video. I apologise if you're getting cross with me for the long videos. The approach we take, frankly, is to do the very best puzzles that we can. And you'd have to try very, very hard to convince me that that isn't an absolutely world-class, historically brilliant Sudoku puzzle. It is fabulous, ridiculously good. That said, if anybody out there, somebody like Marty or Dorlir, can set occasional puzzles where we can do them in 25 minutes, we'd love to. We'd love to introduce more of those as well. It's just, that deserves all the plaudits it can possibly get. Incredible. That is an incredible. I mean, how long ago does it feel like we were doing that weird set stuff? Which I probably, again, there were many bits of that where I don't think I quite grasped the perfect way to see it. I think it might have been necessary to start with these weird 2x2 thingies, these things, and where they go in their respective rows and columns. I'm not sure. I might take another look at it later. But it's a fantastic puzzle, whatever, and I am very relieved to have got through it. Let me know in the comments how you got on with it. I enjoy the comments, especially when they're kind, and we'll be back later with another edition of Cracking the Cryptic.